Alright, Kobe. Even though you're out for 2 weeks, still teaching the class. So, finishing the PowerPoint. So, last time we talked about angular momentum. And I introduced momentum a little bit. We'll go into more momentum later. But all you really need to know is energy is conserved. It doesn't change. It's constant. It can transform from one object to another, or transfer from one object to another. It can transfer from potential to kinetic, but it doesn't change. Momentum, linear momentum, is constant. It can transfer from one object to another, but it never changes. The total momentum of a system is constant. And angular momentum, something spinning, is also constant. Whenever something slows down and stops spinning, it transfers that angular momentum to something else. Now, because Earth is very massive, you don't really notice the spinning being transferred into Earth. But if you were to spin a quarter on a desk, the quarter's spin, or angular momentum, would be transferred to the molecules of the desk, causing them to move in more circular motion, be twisting and spinning, and then that'll eventually go into air molecules in the air, into the ground, into the earth, and you don't really notice it. But the important thing is angular momentum is constant. If something is spinning, that is conserved. I said last time, for the bell rings, that there is a pseudo vector. The only thing you need to know about the pseudo part is that it's not a true vector because it depends on your frame of reference. But like I said, you don't really need to know about pseudo. Just know that it's a vector. It has a certain direction. So if something was spinning clockwise, we can do something the right-hand rule. We wrap our fingers around in the same direction it's spinning, and we point our thumb down. So this would go down into the page. That's where it would be pointing. So angular vectors and torques, any rotational stuff is weird because the vector, the pseudo vector, is pointing in not in the same plane. It really introduces a new dimension. If we have clockwise, wrapping my fingers in the same direction, my thumb will point up toward the camera, so up in the air, out of the page. If we had it more like this, so wrapping my fingers around, the vector will point to the right. And if I had it spinning the opposite direction, so wrapping my fingers like that, it would point to the left. Now, this vector represents the angular momentum. And this is constant. I will say that there's going to be some effect. We'll see this in a little bit. But the vector stays, there's going to be some precession here in a little bit, but I'll say too, because we're adding two vectors together. But what would happen if you rotate a bicycle wheel versus keeping it stationary? I wanted to do this experiment in class, but let's look at this bicycle wheel here.
Which, before we start, we'll leave it stationary and see what happens if I dangle it.
So this has a bearing in it, and this wheel can rotate freely, or this handle can stay put while the wheel rotates around it. But if we were to attach a string to this handle and let the wheel go,
from a string, I'll dangle it from this side, I think. And
you'll see
of
it
course
falls
it
down
wants to
flat.
fall out of it, but if I keep it like that,
It's not rotating, so there's has no angular momentum. So it's just going to fall down. It's going to cause rotations in the string, counteract the rotation of the falling. Some of the angular momentum is extracted from the string, cancel
The string will
out.
hold
When it
it vertically.
rotates, and
It
this will
doesn't want to
stop.
remain like that at all. But if my beautiful lady assistant George would like to,
So spinning
thank
it
you.
up, it's
Okay, does
now
work. George,
going super fast.
thank you. Okay.
See if I can see
Beautiful
what
lady assistant
direction.
George would like to get that spinning.
All right, so it is spinning to the left. So this vector, wrapping my fingers around in the same direction, will be coming out in the screen towards you.
I'm not allowed to do dangerous work, George. Thank you.
Now,
Okay.
angular momentum is
So
going
now
to
I'm
try
going
to
to
stay
hold it
constant. That vector is going to keep
by
trying to
putting
stay
this
in the same
string
direction.
over here and down.
So now that it's spinning, this vector is coming out, and it doesn't want to change. It's going to want to stay horizontal to the ground. So now, if we were to let go of the
It down.
string,
And you see, if I'd left it without the spinning, it would want to stay in the horizontal plane. But
now it is spinning, it doesn't fall over. Counterintuitive, you would think that gravity would be pulling it down, making it want to rotate, but the angular momentum is constant. It can only be transferred into the string and the air. It won't just naturally fall over. Earth's gravity is applying a torque to it, though. So remember that it's if you add torque, you can add angular momentum to it. Without the external torque. So if you have no external torques or external forces, then momentum and linear momentum is constant. But Earth's gravity is applying a small torque. It's kind of robbing some of the linear momentum from Earth's spin, which ends up
actually,
causing
the
it to
angular momentum
precess.
wants to keep in the same direction. Unfortunately, it tries to tip over. When it tries to tip over, it goes round in a circle. But it doesn't want to fall off. This is a very, very stable arrangement. Well, if you're riding a bike and the bike is going along and you suddenly tip over, it doesn't really want to carry on in the same direction. It would prefer to revert back to the vertical. And you design the bike wheels and the front forks in such a way that it leans you back into the right direction. So
this is the reason why you can ride a motorcycle or a bike without falling over. Without the conservation of angular momentum, it would be almost impossible to keep something balanced on that small little wheel. Another thing we can do, I think this video shows it very well. So he has the wheel, so it's spinning in some direction. It's spinning around this way, so wrapping your fingers around in the same direction. The vector is pointing upward.
Nothing crazy happens. But when I flip it,
And when he flips it, again, the total angular momentum has to stay constant. So here you can really see that the angular momentum is transferred from the spinning wheel into the person.
flip it back, and I stop. Flip it, I spin. So the question is, why am I spinning? So I have to force the wheel to turn over. Now Newton's third law says that for every force, there's an equal and opposite force acting as well. So when I force the wheel is applying force equal and opposite onto me, causing me to turn. So the same thing applies when I'm on the ground, but the friction between my shoes and the ground stop me from spinning. So another way to explain what's going on is through conservation of angular momentum. Now, angular momentum is something that tells you how hard it is to either start or stop something from spinning. And it depends on two things. One, how fast it's spinning. We call that the angular frequency. Two, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm going to teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at negative L. But when you flip the wheel now has positive L. So the whole system needs to stay at negative L because of conservation of angular momentum. So I need to spin with angular momentum of negative 2L. That's why I spin the other way.
So angular momentum is conserved. So let's look at this. So for an object that is small compared to the radial distance to its axis, the magnitude of angular momentum is mass times tangential speed times radius. Again, momentum, linear momentum is mass times velocity. Rotational equivalent to mass is inertia, and rotational equivalent of velocity is omega. And omega you can solve for its tangential speed divided by radius, and inertia is mass times radius squared. They cancel. I showed this yesterday in class. So an external net torque is required to change the angular momentum of an object. Ignoring external torques, it stays constant, but if you include an external torque, it can change. An object of a system of objects will maintain its angular momentum unless acted upon by external net torque. This is equivalent to Newton's first law, but for rotational. Suppose you are swirling a can around and suddenly decide to pull the rope halfway in. We solved this yesterday. You change the radius to a half, so it'd be dividing by half, which becomes double. So the law of conservation of angular momentum states if no external net torque acts on a rotating system, the angular momentum of that system remains constant. Just like the conservation of linear momentum, if no external force acts on a system, the total linear momentum stays constant. So I showed this when a ballerina or an ice skater is spinning. If they pull in their arms, if they have their arms out to begin with, they're changing the distribution of mass. Inertia, rotational inertia or moment of inertia, is how the mass is distributed. If you decrease the radius, you're decreasing the inertia. But because angular momentum has to stay constant, if you decrease the I, you have to increase the omega. So suppose you pull the weights inward, the rotational inertia of the man reduces to half. If the rotational inertia reduces by half, then the angular velocity would have to double to counteract it. So the main equations we'll be using is we have tangential velocity. dt is equal to the radius times omega. And radius is in meters. Velocity is in meters per second. And omega is in radians per second. So, for example, let's say that we have a ball attached to a string and it is rotating around in a circle. So let's say the string is 2 meters and it is rotating at a speed of, let's say, let's do 60 RPMs. So omega is equal to 60 RPMs. Note, this is not radians per second. Our R value is 2 meters. If we were to imagine that this is that's moving in a straight line, this tangential line being parallel touches is the tangential velocity. To calculate the tangential velocity, we need to first convert this into radians per second. So, 60 revolutions per 1 minute. So we need to get this in radians per second. So first, easiest thing is to get rid of the minutes. We know that 1 minute is equal to 60 seconds. A minute divided by a minute cancels each other out. So now we're in revolutions per second. A full circle, so a full circle is 360 degrees, r 2 pi, r 1 revolution. So we can convert revolutions into radians by multiplying by that ratio. So there are 2 pi radians in 1 revolution. A revolution divided by a revolution cancels each other out, leaving us with radians per second. So we get 60, you can ignore the ones, times 2 pi divided by 60, and this is in radians per second. So that is just equal to 2 pi. Is equal to 6.28, 31853 radians per second. And our equation is tangential speed is equal to radius, omega, so 2 meters, divided by 6.28. 2831853 radians per second. And remember I said radians is a fictitious unit. It's a meter divided by meter and canceled out. Usually we don't even write the word radians here. We usually just put in 2 pi or just not write the units. Because when we do this, this is going to end up with meters per second. The radians just vanishes because it's not a real unit. So 2 meters times 2 pi is 12.56637 meters per second. So the linear speed at which the object is moving is a little over 12 meters per second, between 12 and 13. Our other major equation is centripetal force. Note that if you were to go into a rotational frame of reference, the force would be outward going. It's the same equation for centrifugal force. They're both equal. And that is centripetal force or centrifugal force is equal to mass times your tangential speed squared over your radius. We also have, remember that tangential speed is equal to r omega. We could plug that in. That's equal to m r squared omega squared over r squared divided by r cancels each other out, leaving us with just 1r. So this could also be written as mr omega squared. So let's do a few examples using centripetal force. Suppose a 2,000 kilogram car is traveling at 20, or let's make it 30, 25 meters per second. Nicole, you mind closing the door? Around a loop or circle with a radius of 50 meters. How much frictional force is required so the car doesn't slide off the road? Well, that's the same as the centripetal force. So centripetal force is equal to mass times tangential speed squared radius. The tangential speed is 25 meters per second. The mass is 2,000 kilograms. And the radius is 50 meters. Plugging that in, we get a force of 25,000 kilogram meter per second squared, which is the same thing as Newton. So 25,000 newtons. That is a lot of force. Probably the car wouldn't be able to make that turn. So let's do another example. Suppose an object has a centrifugal force of 500 newtons going around a 10 meter wide circle. What, or I should say, via a string. So a string is attached to it. The circle is 10 meters wide, and we have a string attached into the center, and the object is here. What speed would the object be traveling at if the string broke? So if the string broke, the object would be moving in a straight line with some speed that's just a tangential speed. So we're solving for the tangential speed. So Fc equals mass times velocity t squared over r. We're solving for dt. So multiply r to both sides. That cancels it on this side. We're left with r times Fc equals mdt squared. Divide by mass. Cancels it on this side. So r times force divided by mass is equal to dt squared. And so pulling this up, we have dt squared equal to r times force over mass. To get rid of the square here, we can take the square root of both sides. That cancels out this. So the tangential speed is equal to the square root of r Fc over mass. And I left off mass. Let's make the mass of the object 25 kilograms. Say 25 kilogram object. So that would equal the radius. The radius would be 5 meters. Mass is 25 kilograms. Centrifugal force is 500 newtons. And note, whenever you take the square root, this would be plus or minus. Right now, I'm asking for speed, so the direction doesn't matter. We're just looking for the magnitude. And that would equal 100 meters per second. Looking over the homework, some notes, mega and radians. So a revolution per second is the same thing as a cycle per second, usually abbreviated as CPS. You can also have a revolution per minute, or RPM. So if you wanted to calculate, so if it is in cycles per second, so 1 cycle per 1 second, so we know 1 full cycle is 2 pi. When you multiply by the ratio of 2 pi by 1 cycle, cycles cancel out, and again, imaginary radian unit here, that's just equal to 2 pi times your cycles per second. So to convert into radians, omega radians is equal to just 2 pi times omega in cycles per second. And if you want to convert into, from RPMs, so we have 1 rev per minute, you multiply by 60, multiply by 1 minute over 60 seconds. Minutes cancel out. Then you do 1 rev is equal to 2 pi. And so basically, omega radians is equal to 2 pi over 60 omega in RPMs. So let's do one example that combines them. Imagine that you had a string that is 1 meter long. And let's attach a 1 kilogram object. And let's spin this around in a circle at a rate of, let's see. Let's make it 2 revolutions, or revolutions per second. So imagine that you have a 1 meter long string, 1 kilogram. That's the same thing as 2.2 pounds. So let me look that up. That's about a half gallon of milk. So imagine you had a 1 meter long string and a half gallon of milk, and you spin it around in a circle for 2 times. So it rotates 2 times a second. How strong would you have to be to hold this rope? How much force would you have to hold on to the rope? So force, centrifugal force, the force you're holding onto a string, is equal to the mass times the tangential velocity squared over the radius. And again, tangential speed is just r times omega, which simplifies to mass times radius times omega squared. And omega has to be in radians. So we can replace omega radian squared with 2 pi and revolutions per second. So a cycle per second is the same thing as revolutions per second. So it'd be this formula. So we can plug that in. So omega, is in cycles, equal to 2 cycles per second. So I could just plug that in. Mass times radius times 2 pi times omega in cycles squared. So our mass is 1 kilogram, or radius is 1 meter, times 2 pi times 2 cycles per second squared. That would equal 16 pi squared, which is 157.91367 newtons of force. That would feel like you're holding up 35.5 pounds. So that's the same thing as 35.5 pounds of force. Alright, that's it for the day. I'm going to release a lot of homework for you to be doing while you're remote learning. Also, you're still missing the gravitational homework from several weeks ago. Take a picture of it and email it to me. You can also, for the homework, because there's a lot of writing, you don't have to use Kami. I highly recommend, if you have a printer, printing it out. Or if you have, or if you just want to do it on notebook paper, on the submission form, So when you go into Google Classroom to submit, instead of editing the document with Cami, you can just attach pictures. Just make sure the pictures are legible, not super blurry, of your work to submit back. It's way better than doing trying to type it all using Cami.